Okay, Bismillah Rahman Rahim. Now, next topic is lining of irrigation canals. Canal whose prism has been protected with impervious material or nearly impervious material, mainly to stop seepage through it, is called a lined canal. Lining of canal means that the earthen surface of the channel is lined with a suitable unerodable lining surface such as concrete, tiles, asphalt, etc. So what is the necessity for lining of irrigation canals? Lining of canals is necessary to minimize the seepage losses in canal, to increase the discharge in the canal section by increasing the velocity. So how the velocity will increase? Because the resistance to flow, that will decrease. So as we already know that Q is equal to AV. So if resistance to velocity decreases because of the lining, so velocity will increase. This will result into increase in the discharge. To prevent erosion of bed and sides due to high velocities. To reduce maintenance of canals. Because if the channel is unlined, the maintenance requirements will be more as compared to lined canals. So these are the various factors that necessitates lining of canals. Advantages of canal lining. Although the cost of construction of a lined canal is many times greater than that of unlined canal, yet the advantages of lining are so obvious and so significant that construction of a canal with lining becomes financially feasible. So lining of canal has high initial cost, but the advantages are so significant that construction of canal with lining becomes financially feasible. So the main advantages derived by canal lining are: the lining of canals prevent seepage loss, and thus more area can be irrigated by the water so saved. The cost of irrigation is therefore reduced. The lining of canal is an important anti-waterlogging measure. So because if we have unlined canal, there will be seepage, and as a result of that, that water can raise the water table in that area, and that can result into water logging. So water logging, as I already explained before, that it is the water table if it is raised to the root zone or intersects the ground surface, so that is known as water logging. Because of water logging, land is not productive for agriculture. So lining of canal, it prevents the seepage loss. So as a result, this lining of canal is an important anti-water logging measure, as it reduces seepage to the adjoining area. The lining provides a smooth surface. The rugosity coefficient therefore decreases. The resistance to flow also decreases, and hence the velocity of flow in the lined canal increases. The increased velocity minimizes the losses due to evaporation, because the water will flow with more velocity. So evaporation rate, that loss will be minimized, because if the water stays in the canal for more time, then the losses due to evaporation, that will be more. The increased velocity helps to provide a narrow cross section for lined canals, and the reason is, as I said, that we have area that will be equal to discharge by the velocity. So if the velocity increases, then the area should decrease. So the increased velocity helps to provide a narrow cross section for lined canals. Higher velocity prevents silting in the canal. Lining reduces maintenance costs and possibility of bank breaching due to increased stability of section. Lining of canal prevents or reduces the weed growth. You can see here that in the unlined channels there could be weed growth. Weed mean unwanted plants that normally grow in the soil when water is available. So by lining of canal, the weed growth, it can be prevented or reduced. Canal lining prevents water to come in contact with harmful salts during transit. As the water moves from the source to the agricultural fields through these canals, so the soil, it can contain harmful salts that are sold in the water carried to the agricultural fields. So canal lining prevents water to come in contact with harmful salts during transit. We also have certain disadvantages of canal lining. The canal lining has certain disadvantages. It requires a heavy initial cost. Lining being permanent, it is difficult to shift the outlets very often, because from the canal we supply water to the different areas, to different farm fields. So for that we need the outlets. So lining being permanent, it is difficult to shift the outlets very often. It is very difficult to repair the damaged lining. A lined section is without a berm. We discussed this in the previous lecture. The additional safety provided by the berm for vehicular and pedestrian traffic is therefore absent in a lined canal. So these are some of the disadvantages, but the advantages are more. So that is why canal lining is financially feasible. So we discuss different types of canal lining. Various types of canal linings which are commonly adopted can be divided into two broad categories. Hard surface linings. So these include concrete lining, shotcrete lining, brick lining, asphalt lining, boulder lining. And we have another category, that is earth type linings. So this include soil cement lining, compacted earth lining. So these are the types of canal linings that are commonly adopted. We have other types also that you can read in the irrigation books. So we will discuss these, but we have other types of canal lining also in use. So we have concrete lining. Now it is best suited for main canals. It has high initial cost, but it has long life and minimum maintenance cost. Concrete lining, clear? A thickness of about 5 to 12 centimeter and stable side slopes between 1.5 to 1 to 1.25 to 1 are adopted. Now, Ghazi Barota hydro power project holds the record for the biggest concrete lined channel in the world. So the Ghazi Barota hydropower canal, which runs from Ghazi to Barota, so it is concrete lined channel. The channel is 51.90 kilometer long with a concrete lining and design flow of up to 1600 cubics at a water depth of 9 meter. It has a bottom width of 58.4 meter and the power channel has a nearly contour alignment with hills on the left side and the land naturally draining towards the Indus River on the right side. So the design flow is 1600 cubics, longitudinal slope is 1:9600, length is 51.906 kilometer, clear, 51.90 kilometer. Full supply depth is 9 meter, bottom width is 58.4 meter, side slopes are 2 to 1 and lining thickness is 135 millimeter. So Ghazi Barota hydropower project holds the record for the biggest concrete lined channel in the world. This you can see this source here, it is written, this information is taken from here, WAPDA website. So you will find this information here. So this concrete lining you can see here. This is concrete paver machine. Next we have shotcrete lining. So it consists of cement sand mortar in the ratio 1:4. The thickness of this type of lining varies from 2.5 to 6.5 centimeter. This is just a cement mortar you can see here that is under pressure from a nozzle, clear. So wire mesh reinforcement is clamped to the channel surface before applying the shotcrete. You can see here the wire mesh reinforcement, it is clamped to the channel surface before applying the shotcrete. So convenient for lining small sections, for repair of old linings, and for placing linings around curves or structures. So this is shotcrete. So this is nothing, it is just a cement sand mortar 1:4 that is provided under pressure. Clear? Next we have brick lining. So it consists of a single or double layer of brick masonry. The size of brick is restricted to 30 by 15 by 5 centimeter for convenience of handling. It is hydraulically as efficient as concrete lining. In case of failure, repair can be done easily. Brick linings are by far the most widely used lining in Pakistan. Asphalt lining. Controlled mixture of asphalt and grade aggregate mixed and placed at a high temperature of 200 degrees centigrade. It is covered with a 30 centimeter layer of earth material for protection. The mix can be placed with a machine like that of concrete. Boulder lining. Suitable where stones of required specification are available in abundance locally, used for lining of earthen canal cross section. To reduce the resistance to flow, a 20 to 25 millimeter thick cement plaster is provided as a finishing surface. Now you can see here, this is boulder lining. Next we have the soil cement lining. Soil cement linings are constructed with mixtures of sandy soil, cement and water which harden to a concrete-like material. The cement content should be minimum 2 to 8% of the soil by volume. Compacted earth lining. Soil graded to obtain the required characteristics and containing enough fine so as to make it impervious is thoroughly compacted at optimum moisture content. Thickness of lining 30 to 90 centimeter. This type of lining is used where suitable soils are available. Next we discuss maintenance of irrigation canals. After the construction of irrigation system in an area is completed, it becomes essential to maintain it for its proper and efficient functioning. There are various reasons due to which the canal may stop function efficiently. These include silting of canal, breaching of canal due to weak banks, weed growth, overflow of canal banks. So these are the reasons due to which the canal may cease to function efficiently. So that's why we need maintenance of irrigation canals. Silt removal. When the silt is deposited on the bed and sides, the capacity of the canal reduces. It is better to exclude silt by providing silt excluder and silt ejector. So silt excluder and silt ejector we will study in the next chapter, that is diversion headworks, in detail. The following measures are adopted to remove the silt. So silt can be removed by flushing, silts covering fleet, bundle of thorny bushes, iron rakes, reduction of area of flow, stirring by water jet, dredging, excavation. So you can read about the detail of all these methods for silt removal. I will discuss a few of them. So flushing. Flushing of the canal with clear water will lift up deposited silt. Absolutely clear water should be used for flushing, but if this is not available, then the water which contains minimum quantity of silt should be used for flushing. Stirring of silt by water jet. A pump fitted with a pipe and nozzle is placed on a barge. Barge means the flat-bottomed boat. Flat-bottomed boat. The high velocity jet is directed to the bed to stir the silt and prevent silting. Excavation. The silt deposited in a channel is cleared off by manual labor. The method is quite costly as it requires recurring expenditure. Every year you have to arrange the labor to clear the silt, so it is quite costly as it requires recurring expenditure. This method is generally adopted for silt clearance in distributaries and miners. The silt must be deposited clear of the channel. When we remove the silt from the channel, it must be deposited away from the channel. So should not be placed on the banks, for example, top of the banks, so that it does not find its way back to the channel. So this is how the silt can be removed. But later on, this should be removed from the bank top so that it does not find a way back to the channel again. Next we have weed control. Water weeds are unwanted plants that grow abundantly in water under certain favorable conditions. They tend to reduce the discharging capacity of channel by reducing of the channel section and velocity of flow. So definitely when we have these weed unwanted plants in the channel section, sides or bed, so they will reduce the discharging capacity. How? By reducing the channel section and velocity of flow. The silted canals provide excellent base for weed growth. Weed removal may be done by plucking them by hand and burning them when canal is dry. Strengthening of canal banks. To prevent breaching of the canal bank, it should be strengthened properly so that valuable loss of irrigation and property is prevented due to breaching a canal section. There are different methods of strengthening a canal bank. It can be done by external silting system, internal silting system, formation of bake berm. So again, you can read more detail about these methods from the textbook. I will explain one of the method here. Internal silting system, sometimes when a canal reach runs in filling, the banks are subjected to water pressure. To avoid damage, the banks must be given extra strength by increasing their sections. Favorable conditions are created to cause silting internally. Sufficient wider section is provided and a part of it later gets silted. So when you provide wider section, so as to allow the silting to happen, clear, this must be for a new channels only. Otherwise, in old channels, then what will happen? The discharge will be significantly reduced, and this is what we studied, the silt removal. Clear? So sufficient wider section is provided, and a part of it later gets silted, forming the additional bank. Such a method is possible only for new channels. To accelerate silting, low submersible spurs. Spurs are just projections from the sides of the canal or in rivers also that we provide. We will study spurs in detail in diversion headworks. So these are just projections. The idea is that we have this bank of canal or river, and these projections are provided, of course, of material. And what is the idea? That the water comes here, it becomes stationary, then it moves away from the bank, and this is how the banks are protected against the erosion. So for this purpose we provide these spurs. So because we want to accelerate silting, we want to slow down the water so that the silt is able to settle down. So low submergible spurs projecting from the banks into the channel may be constructed. So you can see here that internal silting system, we allow the silting of the water from which carries the silting, we allow this silting to settle down and form this silted bank, and that way it strengthens the canal banks. So for this purpose, sufficient wider section has to be provided to allow this silting, and still we have the design discharge. Next we have canal breaches. Canal breach is an opening or a gap developed in the canal bank due to erosion of some portion of the bank. So these are canal breaches. You can see here, this is the canal breach, opening or gap that is developed due to erosion of some portion of the bank. When once water starts flowing out of such breach, it starts becoming deeper and wider unless remedial measures are taken to plug the breach. So you can see here, because of the breaching, then the water will flow to the adjoining area, and the adjoining area can be flooded, and it can cause damage to the properties. So canal breach. So when this happens, what we have to do? The reasons for canal breaching, why canal breaches occur? Breaching due to defective design and construction of the bank. So due to defective design and construction of the bank, it can result the canal bank is not strong enough to resist the water pressure, and breach occurs. Breaching due to exposure of saturation gradient. This we discussed in previous lectures. So the soil particles on the outer slope are dislodged and flown away along the seeping water. A cavity is thus formed in the bank, which ultimately develops into a breach. Breaching due to rush of water through rate holes. So the rates, they make holes in the canals also. So breaching due to rush of water through rate holes, shories, lying near the shore, shories. Piping near downstream toe may ultimately cause subsidence of canal banks. And a willful cut in the canal bank, either for unauthorized irrigation or for allowing the flood water to get into canal to save an area from submergence. So these are the reasons for canal breaching. So when the canal breach occurs, then how we close the banks, closure of banks. You can see here how we will close now this bank. So immediately after a breach occurs, the canal discharge should be diverted to a nearby escape channel on the upstream side, or the canal should be closed from the head to stop the overflow completely. But this second option, that is to stop the water in the canal from the head, many times it is not possible due to close the canal from the head, is the irrigation of the area in between may suffer. In cases of small miners and distributaries, a breach may be closed by dumping huge quantities of earth instantaneously from both sides of the gap. So in case of small miners or distributaries, huge quantity of material can be dumped here from both sides of the gap layer in order to close the breach. In case of bigger canals such as branch canal, the above procedure cannot be adopted. Why? As the discharge from such a canal is large, huge, and may completely wash off the dumped soil. So in case of miners or distributaries, we can dump from both sides this breach with huge quantities of earth. But in case of bigger canals such as branch canal, then this cannot be adopted. Why? Because they carry huge quantity of water and the material will be washed off. So what to do in that case? In such a case, it is necessary to first of all reduce the flow through the breach. This should be done by driving a double line of stakes or wooden piles, bellies, in the opening of the breach. This is the canal here. So first of all, this is the breach. First of all, we have to provide double pile line here. You can see here, this is double line, this one line and then another line, double pile line here, that must be provided to reduce the flow of water. So by driving a double line of stakes or wooden piles in the opening of the breach, the space between the pile lines is filled with planks and or bushes, etc. The filler material can be secured by placing sandbags on top. It says that in here, put bushes, etc. here. And to secure the material on top, we can place the sandbags for stability of this double pile line. Sandbags are placed here. By placing sandbags on the top, if the breach is very wide, another line of defense may be provided. This will reduce the inflow from the breach. Then collect a sufficient amount of earth on both sides of the gap. The earth collected should either be from spoil bank nearby or from borrow pits. So we discussed this in the previous lecture. This earth material is then dumped up instantaneously from both sides of the gap to form a ring bund on the outer side. You can see here, this is a ring bund. So the material is dumped. You can see here, material is dumped from this side and from this side, so that a ring bund is formed. And then this will continue till the whole breach is closed. To form a ring bund on outer side. The opening is then properly filled with suitable earth in layers, each being properly compacted. And after closing the breach, the bank so formed is inspected carefully for few days to watch its proper functioning. So this is how we close the banks in case of bigger canals. Next, we discuss design of lined canals. So far, the Kennedy theories that we discussed, those are applied for design of unlined canals. And remember, we have other methods also for the design of unlined canals. But we discuss the Kennedy and Lacey theory because these are included in your syllabus. But we have other methods also available to design the unlined canals. Now, lined canal design, this is not included in your syllabus. But I just briefly discuss it here so as to refresh your memory. Actually, the design of lined canal is what you have studied in your hydraulic course. Same procedure, same equations, etc. So I just briefly discuss it here, although it is not given in your syllabus, just to refresh your memory. So canal cross sections, generally two types of lined canal sections are adopted: triangular section, clear, or curved channel, and trapezoidal section or flat bottom shaped channel. Now the side slopes are so selected that they are nearly equal to the angle of repose of the soil, so that no earth pressure is imposed on the lining. So angle of repose, as you might have studied in geotechnical engineering, if you dump the soil and compact it, so you can see that we provided the slope here. We provided this slope here. Now this slope, the material will not fall down because this slope is stable. But there is certain slope if we further dump the material, let's say up to here, and this is unstable. So the material, it will fall down. Clear? So the maximum slope that we can provide and still the material is stable, that is angle of repose. Clear? So the side slopes of the lined canal are so selected that they are nearly equal to the angle of repose, so that no earth pressure is imposed on the lining. The corners are rounded off to improve the hydraulic efficiency. It means that, let's say we have a triangular channel here. So what will happen is that the corners, they are rounded off. So instead of this, what will be the channel section? It will be like this, rounded off. To improve the hydraulic efficiency, because you see here the wetted perimeter, that is reduced. And you already studied that when we have the velocity as per the Manning's formula, if you remember from hydraulic course, we have this hydraulic radius, that is 2/3, and we have this S 1/2. So if the hydraulic radius, that is reduced, this wetted perimeter, if this is reduced, so hydraulic radius that will be increased. Hydraulic radius is equal to area divided by the wetted perimeter. So here the wetted perimeter that is reduced, so this will increase R, and when R is increased, so it will increase the velocity, and we have Q is equal to AV, the discharge will be maximum. It will be increased. Just like you studied the concept of best hydraulic section or most efficient section in your hydraulics course. So that is why the corners are rounded off to improve the hydraulic efficiency. You can see here the wetted perimeter is reduced. So this will increase the hydraulic radius, and as a result the discharge will be increased. Triangular section is adopted for small discharges as it is best discharging section. For higher discharges, trapezoidal section may be adopted. The limiting velocity is taken as 1.8 meter per second. Then the circular section can be adopted only if the discharge is less than 85 cubics. This is what is written in irrigation book by Engg. The limiting velocity, the permissible velocity, is taken as 1.8 meter per second if. Then circular section can be adopted only if discharge is less than 85 cubics. So we have triangular shaped or curved channel. You can see here that it is rounded. The corners are rounded here, and we have the side slopes and the full supply depth. So the bed is circular with its center at the full supply level and radius equal to full supply depth. The sides are tangential to the curve. So we have to develop formulas for the wetted perimeter and for the flow area. So you can see here for the different side slopes 1 to 1, these are the equations that can be conveniently used while solving the problems. 1.5 to 1, then these are the formulas, and 1.25 to 1, these are the equations that can be conveniently used. If other side slopes are given, then you have to develop the equations for that. Clear? Then we have trapezoidal shaped or flat bottom shaped channel. So this is the trapezoidal channel section. Here you can see the horizontal bed is joined to the side slope of the curve of radius equal to full supply depth. So you can see here radius is equal to full supply depth. Again we have this table, and these formulas can conveniently be used for 1 to 1 side slope, 1.5 to 1 side slope, 1.25 to 1 side slope. Now for these channel sections, in order to design a lined canal section, the following data is required: the discharge, rugosity coefficient N, longitudinal slope, side slope, and the permissible limiting velocity. Clear? So this is the required data. So the procedure for design of trapezoidal shaped channel is given, and similar steps for the triangular channel. So step number 1 is knowing the limiting velocity, rugosity coefficient, the longitudinal slope. Calculate the hydraulic mean depth R using the Manning's equation. You can see here that the limiting velocity, permissible velocity, that will be given. So rugosity coefficient is given, slope is given. So we can calculate the hydraulic mean depth or hydraulic radius. So we have these equations in MKS and FPS system. Now discharge is given and the velocity is calculated, so we can calculate the flow area. So discharge divided by the velocity. Then step number 3 is to calculate the wetted perimeter. We already know the flow area. Clear, the hydraulic radius is calculated in step 1. So we can calculate the wetted perimeter using this formula, area divided by the hydraulic radius. Step number 4 is that for trapezoidal shape section, these are the equations. We can have similar equations for triangular shaped also. So this is the equation. These equations you can read from the textbook, how these equations are developed. I directly write down here for the area A and for the wetted perimeter P. B is the bottom width, D is the depth, theta is the slope, cotangent theta. Theta is this slope here. You can see here, this is theta. So similar steps for triangular channel, but then these formula have to be modified. Now in this equation, you see area we have calculated and wetted perimeter is coming from step number 3. So the only unknowns are B and D. So B is unknown and D is unknown. Now we have two equations in terms of two unknown. B is unknown and D is unknown. So two equation, two unknown, we can solve simultaneously to calculate the value of B and D. Since A and P are known, the values of B and D can be computed by simultaneously solving these two equations. So the value of the Manning's N, so maybe in the hydraulics course you use small n, Manning's formula, but here as per the irrigation books, we have capital N. For line channel, you see type of lining, concrete, this is cast in situ, in situation. Concrete trowel finish, this is the range of the values of N. Cement plastered masonry, this is the range. PCC slabs or tiles, this is the range for the values of N. Brick lining, we have, this is the range. So these are the guideline values given. In a problem, if these type of linings are given, you can assume the values from here. And the permissible velocity, the limiting velocity. So type of lining, cement concrete lining 2 to 2.5 meter per second. This should be adopted as the permissible velocity. Clear? Burnt clay tile lining 1.8 meter per second, boulder lining 1.5 meter per second. So these tables are taken from the irrigation book. So as a guideline values. So let us try to solve one example, design of lined canal. Design a trapezoidal shaped concrete lined channel to carry a discharge of 350 cubics at a slope of 1 in 5,000. The side slope of the channel are 1.5 to 1. The value of N may be taken as 0.014 and assume the limiting velocity is 2 meter per second. So again, we have step-by-step procedure. Let us quickly solve this problem here. We have step number 1. We will calculate the hydraulic radius. So for this, we will use the Manning's formula. So we have the Manning's equation, take care of the system of units. We have this V is equal to 1 by N into R, hydraulic radius 2 by 3. And we have this S 1 by 2. Now you can see that V is given, N is given, S is given. Just plug in the values. Only unknown is this hydraulic radius R. So this is unknown. We can calculate this is 2.79 meter. This is now the hydraulic radius. Next we can calculate step number 2 is area. Velocity is given, discharge is given. So area we can easily calculate. So area A, that will be equal to discharge divided by velocity. So discharge is 350 divided by 2. Area comes out to be 175 square meter. Square meter. This is the area. Now next we can calculate the wetted perimeter. Step number 3. We can calculate the wetted perimeter. So P, that will be equal to A divided by R. So area is 175 divided by R, 2.79. So this comes out to be 62.72 meter. Now step number 4 is we will write down area we have calculated, wetted perimeter we have calculated. So step number 4 is we have this equation for area A. For trapezoidal channel, A is equal to B into D plus D square into theta plus cotangent theta and we have this P that is equal to B plus D, in fact 2 times D because we have 2 sides. So theta plus cotangent theta. Now from where this theta and cotangent theta will come, you see the side slopes are given 1.5 to 1. So we have the side slopes so the side slope, this is the side slope, this is Z and this is 1 vertical. Now we have theta, so you see that this is theta. We have this as the slope, this is Z, this is 1, so this is theta. And this will also be this theta. Clear? So now tan theta this will be equal to 1 divided by z, and z is 1.5. So cotangent theta, what will be cotangent theta? That will be inverse, so this will be equal to 1.5. Now you can easily calculate the theta. Tan theta is equal to 1 divided by 1.5. So from here, this theta, this can be easily calculated, and this comes out to be how much? 33.69 degree. 33.69 degree, because here theta we need to write down in radians, so this can be written in radians as 0.59. This is in radians. Now you see that we can directly put these values. For cotangent theta is 1.5 and for theta is 0.59 in these equations. So this equation A can be written as area we have calculated 175. Area is 175 here. So this will be equal to B into D. This is what we have to calculate, both, plus we have D square, and we have 0.59 as theta here, and cotangent theta is 1.5. So we have 0.59 plus 1.5. So this is equation A. Similarly, we have this equation for P. P we have calculated as 62.72. So this is 62.72. This will be equal to B, and plus we have 2 times theta plus cotangent theta. So if you put here, this will become a D into 4.18. This is 2 multiplied by theta plus cotangent theta here. So this is 4.18. So these are now, this is equation B. So now you can see we have 2 equations in terms of 2 unknown B and D that you can solve. For example, from here we can have B that is equal to 62.72 minus 4.18 times a D, and put this in equation A. Put in equation A. So now by solving, we will get D 2 values, because we have quadratic equation. You can see here D square. So you will get 2 values for D. One will be equal to 26.89 meter. and another value will be equal to 3.11 meter. So you can see here that this 26.89 is not realistic value. So 3.11 meter, that will be a D. So you can put here and calculate a B. So these are now the values. A D is equal to 3.11 meter, and if you put this value, we will get the bottom width, that will be equal to 49.72 meter. So this will be the channel that we designed, the lined canal. So we have this as the D, and this is as the B with the side slopes. And also in all these problems, do not forget to provide the freeboard that we already discussed in the previous lecture. How much freeboard has to be provided, that will depend on the discharge. So remember that we have to provide the freeboard. So this is a design of lined canal. I just teach it to refresh your memory. Otherwise, remember, design of lined canal is not included in your syllabus. Now, finally, we see that if you remember from the hydraulics, we studied about the best hydraulic cross section. So these are the conditions. You see here, trapezoidal section half of a hexagon, rectangle half of a square, triangular half of a square, and these are the equations that are corresponding to area, wetted perimeter, hydraulic radius, the top width, clear for trapezoidal, rectangular, and for triangular channel. So these equations you have already studied in your hydraulics course. So you see that we can proceed the design under normal conditions, but it can be asked in the question that you consider the best hydraulic cross section. Then you have to use these equations in the solution so that the cross section becomes the best hydraulic cross section for that canal. If it is not asked in the question, we can proceed like this, normal condition. But for best hydraulic section, then you have to incorporate these equations. Clear? And finally, you can see in this video, this is a case study from Pakistan. What are the advantages when we construct a canal? So you can see that how the canal changed the lives of millions of people.